Today's edition of SpaceTime is brought to you by our new sponsor, Brilliant.org. Maths and science done right. Learn to think like a scientist with their carefully curated lists of puzzles and questions. Check them out today and use the link brilliant.org/Stuart Gary so they know you've come from us. Once again, that's brilliant.org/Stuart Gary. This is SpaceTime, Series 20, Episode 73. Coming up on SpaceTime, the best estimates yet for Earth's composition, the new supernova study reframing the dark energy debate, and mountain climbing with curiosity as it ascends the Martian ridge. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Astronomers have made the most accurate estimate so far of the Earth's core, finding it makes up some 32.5% of the planet's total mass. The findings, reported in the journal Icarus and on the pre-press physics website archive.org, are part of a new understanding of the Earth's composition, which will help scientists develop new methods that determine if exoplanets orbiting distant stars are likely to be capable of supporting life. By relating Earth's composition to that of the Sun, researchers from the Australian National University hope to use those comparisons to determine the makeup of exoplanets by looking at the composition of their host stars. To work out the exact composition of a planet, you've really got to be there. But astronomers can work out the composition of stars simply by studying their spectra, the chemical signatures detected in the light coming from those stars. Once perfected, the new technique will allow scientists to focus on stars more likely to have planets with an Earth-like chemical composition. As a starting point, astronomers needed to understand the exact composition of the elements which condensed out of the protoplanetary disk of gas and dust around the early Sun to form the Earth 4.6 billion years ago. The four most abundant elements, iron, oxygen, silicon and magnesium, make up more than 90% of the Earth's total mass. However, determining precisely what the Earth is made of has proven to be somewhat more difficult. Seismological studies based on earthquakes provide a detailed picture of the planet's internal structure, including information on the densities of the inner and outer core, the lower mantle, and the upper mantle and crust or lithosphere. But it's difficult to convert this information into a really detailed chemical analysis. The deepest humans have actually drilled down into the Earth is the Soviet Union's, now Russia's, Kola super-deep borehole, which has reached a record depth of 12,262 metres, that's 40,230 feet. But when you think about it, that really only scratches the surface of a planet with a radius of 6,400 kilometres. The authors developed new estimates of the Earth's composition based on a metadata analysis of previous estimates of the mantle and core, and a new estimate of the core's mass, finding it makes up 32.5% of the planet's total mass with an error of plus or minus 0.3%. One of the study's authors, Associate Professor Charlie Lineweaver, says the team's proud of all the work they've done, especially that involving determination of the plus or minus 0.3% error bar. That's because when you're interested in exoplanets, the error bars become really important. When the authors looked at the available literature to try and get the best understanding they could of the Earth's composition, they found that a lot of effort had been put into determining the composition of the mantle, a little bit of effort had been put in determining the composition of the core, but almost no effort had gone into trying to put those two together. The problem was made even worse because previous researchers had all used different models and haven't been quantifying the error bars associated with each of the models. Lineweaver says that means researchers have determined what the mantle's made of and what the core's made of, but he says no one's taken the trouble to see what the error bar of the mass fraction of the core is. And the thing is, without the error bar, you really can't put them together, and if you can't put them together, then you really don't know what the bulk composition of the Earth is. The authors also found abundances of magnesium, tin, bromine, boron, cadmium and beryllium were significantly lower than previous estimates for the bulk Earth, while abundances of sodium, potassium, chlorine, zinc, strontium, fluorine, gallium, rubidium, niobium, gadolinium, tantalum, helium, argon and krypton were all significantly higher. The new analysis tells us what the Earth is really made of. The next step is determining exactly what the Sun's composed of, and then comparing the two. Lineweaver and colleagues can then figure out how the Earth became devolatilized to become what it is now. And it's that devolatilization pattern which the authors are really after. In other words, you take something like the Sun, Get rid of the hydrogen as well as the helium and other noble gases, and what you're left with is a devolatilized chunk of stuff which became the Earth. And it's that devolatilization pattern which the authors are looking for. The team's ultimate goal is to use their comparison of the Sun and the Earth to determine the chemical composition of terrestrial planets in the Alpha Centauri system. Lineweaver says science knows virtually nothing about the planets in this system, and this technique will allow him to make lots of predictions about what those planets are likely to be like. For example, magnesium and calcium ratios in these worlds will be different, and you'll have different amounts of orthopyroxene, which changes the amount of water the planets can hold on to. Lineweaver says the research will provide a semi-universal devolatilization pattern, which can then be applied to help determine the chemical compositions of terrestrial exoplanets around other stars. You see, even though we can't directly see these terrestrial exoplanets, the technique will allow astronomers to make predictions about what they're most likely made of. Lineweaver points out that statistical predictions tell scientists that pretty well every star in the sky has some kind of planetary system around it. He says the problem then simply becomes one of determining what kind of terrestrial planets are likely to exist in the habitable zone around each star, and whether any of these worlds are Earth-like and capable of supporting life.
You're talking to two astrophysicists and an Earth scientist who haven't been doing this their whole careers, and so why in the world do we do this? And that was, the reason is we're interested in exoplanets, and we're interested in exoplanets, what the chemical compositions of them are, whether you can live on them or not. Now, one way to get at the exoplanet compositions is to look at the compositions of the stars, their host stars, which we can get the chemical compositions of from the spectra. So, that's the main goal. Hey, let's get at what the Earth-like planets in the whole universe are like based on the elemental abundances of their stars. And then we said, well, I guess if you're going to do that program, you're going to have to calibrate that on the Sun and the Earth. So that's where we started. And then we say, okay, let's look in the literature to get the best composition of the Earth available. And then if you do this, you'll find out that lots and lots and lots of effort has been put into getting what the mantle is made of. And then a little bit of effort has gone into what the core has been made of, and almost no effort has gone into trying to put those two together. And so we said, this is ridiculous. You mean we're going to have to do this ourselves? And so we had to say, yes, we did this. So we have to do it ourselves. And then we found out this was just a minefield of controversy, because over the past 20 or 30 years, people who have been doing this have been using different models, and then they haven't been quantifying their error bars associated with those models. So bottom line is, here's what the mantle's made of, here's what the core is made of. How do you put them together if you don't have an error bar on the mass fraction of the core? Over the past 20 years, people have said, you know what, the core of the Earth is 32% of the mass of the Earth. Other people said, no, it's 33%. Other people said, no, it's 32.5. But no one has taken the trouble to say what the error bar on that number is. And without that error bar, you can't put them together. And if you can't put them together, you don't know what the bulk Earth composition of the Earth is. So that's what we had to do. It's like an exercise in, it's more than an exercise. We had to also use a different mass of the Earth, because the people who were doing it earlier were using an inappropriate one. The mass of the Earth has grown over time.
How does that affect the crust of the Earth, however, which is where, if there is life, that's where most of the larger life forms should exist? I know your own research has shown it goes pretty deep below the crust.
Right. Well, when you're talking about the bulk composition of the Earth, the tradition has been, and it still remains, you divide the thing into the core and what's called the primitive mantle. Now, primitive mantle means it includes all of the volatiles and all of the crust and all the rest of the mantle. So you're not making a distinction between that. That's a very complicated process, but if you're not concerned about this separation, then you don't have to do it. And that's what we didn't do, and no one else has done that either. In other words, we're talking about the bulk Earth, and therefore it doesn't matter whether it's segregated radially or not. What you want to know is how much hydrogen, how much helium, how much calcium, how much iron, how much nickel in the entire thing, including the atmosphere, which is almost nothing of the mass.
And by doing that, how does that help you determine which exoplanets you should be looking for?
Okay, well, that's in the next paper that is under review. First of all, so this is the Earth. Then we have to say, well, if you're going to compare the Earth to the Sun, you have to know what the Sun is made of. And so basically we did the same thing with the Sun, and then we compared our Sun, which we consider to be the best estimate of the Sun, with this best estimate of the Earth, all of this with error bars, and then we could figure out, okay, how did the Earth get devolatilized to become what it is? And that devolatilization pattern is what really we're after. And that, in other words, you take something like the Sun, you get rid of hydrogen, helium, and noble gases, and then you're left with a devolatilized chunk of stuff, and that is what became the Earth and the other rocky rocky planets, and that's what we're really after.
And you adjust for its distance from the sun as well?
Well, we're not really able to do that yet because we have such lousy estimates of what the bulk compositions of Mars and Venus are. We have surface estimates, but those estimates are not nearly as mature as the composition of the Earth. And so you'd have to make many more guesses. We have plotted these, and we're kind of satisfied with what we could do. But instead of trying to do Mars, Venus, and the Earth, we decided to go straight for Alpha Centauri. And so what we're doing now is using our comparison of the Sun with the Earth to figure out what the chemical composition is of the rocky planets around Alpha Centauri, which we will all escape to in about 5,000 years or so.
Okay, well, all right. So what conclusions have you reached based on this research about the Earth's composition?
Well, one conclusion is this mass fraction of the core is something that we had to work on and get an error bar for. So that's new. We have 32.5 plus or minus 0.3, and that 0.3 we're very proud of because it takes a lot of work to get error bars on things like that. Then there are a bunch of elements that are the most significantly different from previous analyses, and those are magnesium and tin and bromium and boron and cadmium. A lot of these are not that important, except the most important ones are the magnesium, for example. That's a very important element that we're getting a different estimate for. Also sodium, potassium, chlorine. These are, when I say important, I mean they're more than one sigma different from the previous estimates, and previous estimates didn't have error bars, so we have to base this on our own error bars.
And also there's some controversy about the ratios of some of the elements, especially near the core mantle boundary too, isn't there?
Oh, yes. There are more controversies than you can shake a stick at, and we had to ignore almost all of them and had to deal with, for example, we were not trying to solve the controversies associated with the umpteen different models for the Earth. What we were trying to do was quantify how different these models were from each other. In other words, put them together and then figure out what the real error bar is, because only if you have an error bar can you combine things and get an estimate of with what confidence can you say the Earth is a devolatilized part of the Sun, because if your error bars are either non-existent or gigantic, then you can't do anything. And so what we did is, for the first time, is quantify these error bars better than anybody has ever done, and that allows us to proceed with the type of analysis that we want. Anyway, it was a long, hard exercise in getting data and people together and then combining it in a new way and then getting what we are calling the best estimate of the elemental composition of the Earth ever made.
And where to next?
Well, the where to next is to use this, like I said in the next paper, comparing the Earth to the Sun in a way that could not have been done before without elemental abundances with error bars. And then that tells us the details of how the Earth formed out of material, solar material. That is the number one thing that we're after, and that's what we've already submitted, and that's under review at the same journal, Icarus. So while we're waiting for that to come through, we're applying this technique, this devolatilization, to Alpha Centauri, and then the goal is to make a prediction about the chemical composition of the rocky planets around Alpha Centauri, which we know almost nothing about, but with this information we can make lots of predictions about what those planets will be like. For example, they'll have something like 20% more magnesium, and calcium ratios will be different, and you'll have a different amount of orthopyroxene, and that changes the amount of water that the planets can hold on to when it's getting buffeted by, the early bombardments. So that's where we're going with this. We want to make a universal or a semi-universal devolatilization pattern that can be applied everywhere in the universe, and to tell us what the chemical composition of the rocky planets are around other stars, even though we can't see these rocky planets and won't be able to see them very well for the next 10, 20, 30 years, we'll still be able to make predictions about what they're made of. For example, right now, if you look at any star at night, the statistical predictions based on what we've been able to sample so far of exoplanets tells us that every star has some type of planetary system around it. On the other hand, we've only seen, out of the 300 billion stars in the galaxy, we've only detected planets around maybe 1,000, 2,000. So that's a tiny, tiny, tiny fraction. But because of the statistics and how you analyze them, we can safely conclude that every star has some type of planetary system around it. The problem then becomes, okay, what kind of rocky planets are there in the habitable zone of this star. And that's really a goal that we're after, because we want to see how many Earths there are, and on these Earths, will there be life? So that's a next question that we have another PhD student working on.
And there are a lot of variables there too. You've got to look at the type of star it is firstly. There's been such a big debate, which actually surprised me, that people are looking at the TRAPPIST-1 system. People are talking about, there could be life on these planets, and yet this is a red dwarf. And you've got to wonder why people are even looking for life around red dwarf stars.
Right. I know they are. You know what? About 80% of the motivation for this looking for life around M-dwarfs is because that's where they can find the planets based using the techniques today. For example, that was based on a transit system. And M-dwarfs are hard to do in transit, but they are easier to find Earth-sized planets in transit around an M-dwarf than they are around a FGK star, like a sun-like star. And that's so in both the two techniques, both the radial velocity technique and the transit technique, it's easier to find Earth-like planets around M-dwarfs than it is around sun-like stars. Because of that, there's an incredible interest in what we can find, and to hell with any of the complications associated with that. The biggest complication in my mind for why these planets, even though they're in the circumstellar habitable zone based on liquid water on the surface of a planet that has an atmosphere, is that the first billion years almost of the life of an M-dwarf consists of a luminosity that decreases by a factor of 100. In other words, any planet which is currently in the circumstellar habitable zone around one of these M stars used to be blasted to hell with high radiation and much hotter than it is now. And so that probably devolatilized all of the rocky pieces that were near to the star, and therefore the idea of having volatiles near them is probably just it's not very plausible. And so that, I think, is the biggest objection in my mind to the habitability of rocky Earth-like planets in the current habitable zone around M-dwarfs.
That's Associate Professor Charlie Lionweaver from the Australian National University and the Mount Stromlo Observatory. And you're listening to Space Time. I'm Stuart Gary. A new study claims the accelerating expansion of the universe due to dark energy may not be real, and instead could just be an apparent effect. The findings, reported in the monthly notices of the Royal Astronomical Society, claims the fit of Type 1a supernovae in a model universe with no dark energy appears to be very slightly better than the fit for the standard dark energy model. Dark energy is usually assumed to form roughly 70% of the energy mass budget of the universe. However, as the name suggests, dark energy is really a mysterious quantity, essentially simply a placeholder for some unknown type of physics. But it's an important placeholder because current models of the universe require this dark energy term to explain the observed acceleration in the rate at which the universe is expanding. Scientists are basing this conclusion on measurements of the distances to Type 1a supernova explosions in the distant universe. These events appear to be further away than what they should had the universe's rate of expansion not been accelerating at an ever-increasing rate. And they can even determine that the accelerating rate of expansion first became a major driving force about 6 billion years ago. However, just how statistically significant this signature of cosmic acceleration is has been hotly debated for almost as many years as SpaceTime and its predecessor Star Stuff have been on the air. So we're now talking around 20 years. Previous debates have pitted the standard lambda cold dark matter cosmology against an empty universe whose expansion neither accelerates nor decelerates. The problem is both these models are assuming a simplified 100-year-old cosmic expansion law known as Friedmann's equation. Now, Friedmann's equation assumes an expansion identical to that of a featureless soup with no complicating structure. The problem is we know that's not a really good picture of the large-scale structure of the universe. The present universe actually contains a complex cosmic web comprising sheets, filaments, and connecting nodes of galaxies and galaxy clusters surrounding vast empty voids. The new study's lead author, Professor David Wiltshire from the University of Canterbury in Christchurch, New Zealand, says the past debates missed an essential point. If dark energy does not exist, then a likely alternative is that the average expansion laws simply don't follow Friedmann's equation. Rather than comparing the standard lambda cold dark matter cosmology model with an empty universe, Wiltshire's new study compares the fit of supernova data in lambda cold dark matter to a different model called timescape cosmology. In timescape cosmology, there is no dark energy. Instead, clocks carried by observers in galaxies differ from the clock that best describes average expansion once the lumpiness of structure in the universe becomes significant. So then, whether or not one infers accelerating expansion crucially depends on the clock being used. Are you in a dense cluster, or are you in the middle of a vast empty void? According to Wiltshire, the bottom line is that timescape cosmology was found to give a slightly better fit to the largest supernova data catalogue than the lambda cold dark matter cosmology. Unfortunately, the statistical evidence is not yet strong enough to definitively rule in favour of one model over the other. But future missions, such as the European Space Agency's Euclid satellite, should have the power to distinguish between standard cosmology and other models, thereby helping scientists to decide whether dark energy is real or not. Deciding that not only requires more data, but also a better understanding of the properties of supernovae, which currently limits the precision with which they can be used to measure distances. And on that score, the new study shows significant unexpected effects which are missed if only one expansion law is applied. Consequently, even as a toy model, the timescape cosmology provides a powerful tool to test science's current understanding, casting new light on some of science's most profound cosmological questions. You're listening to SpaceTime. I'm Stuart Gary. Okay, let's take a break from the show and talk about our new sponsor, Brilliant.org. There are lots of people to thank for supporting SpaceTime, and one group that deserves special thanks right now is Brilliant.org. In fact, if you're at your computer right now, go check out their site, brilliant.org/StuartGary, and see what they're all about. Videos and books give you ideas and explanations, but the thing is, science and maths aren't just spectator sports. The only way to actually solidify learning is with your own exploration and problem solving. For example, when I was at uni, I wasn't just told about equations like Newton's law of universal gravitation or Einstein's mass-energy equivalence. I had to repeatedly apply these laws to solve real problems. And you know what? It felt good. And that's why I think anyone listening to SpaceTime would love Brilliant.org, because they're a problem-solving website that teaches you to think like a scientist. Brilliant.org offers really well-curated sequences of guided questions. And having played around on the site, I can tell you a lot of thoughtful hard work's gone into making these as good as they are. And the subscription they're offering to get a full suite of problems is a really good deal. Plus, there's a whole host of free material to try out. Go and have a play with their astronomy toolbox. I think you'll find it fun. And of course, if you love listening to SpaceTime, you can support the show by going to brilliant.org/StuartGary or follow the links in our show notes or on our website. That lets them know you came from here. That's brilliant.org/StuartGary. Give it a try. And now, back to the show. NASA's Mars Curiosity rover has begun a steep ascent up an iron-oxide-bearing ridge, which has been grabbing scientists' attention since even before the rover's arrival on the red planet back in 2012. The Vera Rubin Ridge stands prominently on the northwestern flank of Mount Sharp, resisting erosion better than less steep portions of the mountain both below and above it. Also known as Hematite Ridge, it was informally renamed earlier this year in honour of the pioneering astrophysicist Vera Rubin. Curiosity Science team member Abigail Freeman from NASA's Jet Propulsion Laboratory in Pasadena, California, who organised the rover's Ridge campaign, says she had the chance to observe the large vertical exposure of rock layers which make up the bottom part of the ridge as Curiosity skirted around the base of the ridge earlier this year. However, while steep cliffs are great for exposing stratifications, they're not so good for driving up. The ascent to the top of the ridge from a transition in the rock layers at the bottom of the rise should gain about 65 metres in elevation. In case you're wondering, that equates to a 20-storey building. The overall climb will require a series of drives totalling 570 metres, more than half a kilometre. Before starting this ascent in early September, Curiosity had gained a total of only around 300 metres in elevation during all its driving time, totaling 17.32 kilometres, from the time it left its landing site in Gale Crater back in 2012 until the moment it reached the base of this ridge. Curiosity's telephoto observations of the ridge from just beneath it show fine layering, with extensive bright veins of varying widths cutting through the layers. Scientists will now have a chance to examine these layers up close as the six-wheeled robotic rover climbs the ridge. Using data from orbiters as well as Curiosity's own approach imaging, mission managers have chosen a series of places to pause for more extensive studies along the way. Of special interest are places where rock layers show changes in appearance or composition. But as with everything in Curiosity's mission, this campaign plan will also be flexible, designed to evolve as scientists examine the rocks in greater detail. In orbital spectrometer observations, the iron oxide mineral hematite shows up far more strongly near the ridge top than elsewhere on Lower Mount Sharp, including locations where Curiosity's already found hematite. Researchers want to get a better understanding about exactly why this ridge is resisting erosion, what's concentrated its hematite, whether those factors are related, and what the rocks on the ridge can reveal about ancient Martian environmental conditions. Curiosity's already been a tremendous success. During the first year after its landing near the base of Mount Sharp, the mission accomplished its major goal by determining that billions of years ago, a Martian lake in Gale crater offered the sorts of conditions that would have been favourable for microbial life. Curiosity has since traversed through a diversity of environments where both water and wind have left their imprint. Vera Rubin Ridge and the layers above it, which contain clay and sulfate minerals, provide tempting opportunities to learn even more about the history and the habitability of ancient Mars. I'm Stuart Gary. You're listening to SpaceTime. The Russian Soyuz MS-06 capsule carrying the Expedition 53 crew has successfully docked with the International Space Station as both spacecraft flew at 28,000 kilometers per hour, some 400 kilometers above the South Pacific Ocean off the coast of Chile. The docking with the orbiting outpost space-facing Russian Poisk module took place just 6 hours after the Soyuz FG rocket launched from the Baikonur Cosmodrome in the Central Asian Republic of Kazakhstan on a fast rendezvous flight path.
I'm getting confirmation the ground propellant feed has been terminated. We'll have one more umbilical to separate. The engines now firing. The launch command issued. These engines now ramping up.
Engine turbo pumps at flight speed, engines at max.
And liftoff. Mark Vande Hei, Alexander Mazurkin, and Joe Acaba lifting off and now on their way to the International Space Station. A little over 10 seconds already into the flight, getting good first stage performance. Soyuz delivering about 930,000 pounds of thrust from those 4 boosters in the core engine.
The vehicle is stable.
Continuing to get good calls. The vehicle stable. Everything looking great as it sears across the Kazakh sky, burning an image across the black.
Pressure is nominal.
This first stage going to burn liquid fuel for the first 2 minutes and 6 seconds into the flight.
Yaw, pitch, roll are nominal.
So the yaw, the pitch, the roll, everything determining the attitude of the rocket, basically which way it's pointing, all looking good. Continuing to get good first stage performance from the Soyuz rocket.
80 seconds. Booster motion control system parameter.
And at this point, the vehicle already moving in excess of 1,100 miles per hour. We're a little over a minute and a half into the flight since liftoff. Still getting good calls on vehicle performance, everything looking great. The next major milestone coming up is going to be that escape tower actually being jettisoned. And just got confirmation the escape tower has been jettisoned. The 4 strap-on boosters have been jettisoned, their job complete. Soyuz already at an altitude of about 28 statute miles, traveling at over 3,350 miles per hour.
The vehicle is stable.
The first stage has done its job. Those 4 strap-on boosters have dropped away. That single core engine now continuing to fire. Getting confirmation from the visiting vehicle officer here that the launch shroud has been jettisoned. So the Soyuz spacecraft now exposed. The rocket's altitude about 48 miles high. And at this point in the flight, as we just passed 3 minutes, the Soyuz already traveling at speeds in excess of 4,700 miles per hour. And again, the core stage is the second stage, continuing to perform as expected. It's 56 feet in length, 13.5 in diameter, and has a single engine with 4 fuel chambers that provide between 178,000 and 222,000 pounds of thrust, depending on the altitude, for its 3 minutes and 28 seconds of operation. This stage is going to continue to burn until about the 4-minute 43-second mark. Then the Soyuz will be ready to do what's called a hot stage technique, and that's when the third stage will ignite while the second is still burning. That's why if there's that lattice structure, that open area between the second and third stages.
250 seconds, your pitch roll are nominal. Everything is nominal on board. The crew is feeling fine.
As you heard, the crew doing fine. The rocket continues to send them into orbit. The second stage still going. And confirmation the second stage has separated successfully.
We also saw the separation of stage 2, and everything is nominal on board.
And so at this point, the second stage has dropped away. The core booster separates at an altitude of about 105 miles. The Soyuz spacecraft now being propelled by the single engine of the Soyuz's third stage. That's going to provide 67,000 pounds of thrust and burn for about 4 minutes and 2 seconds. So the first two stages complete. The third and final stage of the climb to orbit now underway. Everything continuing to go very smoothly with this flight. Crew on board doing well, and the Soyuz continuing its climb to orbit.
380 seconds of flight. Third stage thrusters operate nominally. Everything is nominal on board, and the crew is feeling fine.
Well over 6 minutes now. The crew, the rocket, all doing well.
420 seconds. Your pitch roll are nominal. Everything is nominal on board. The crew is feeling fine.
So over 7 minutes now, approaching the 7.5 minute mark soon, and the velocity of the rocket already about 13,500 miles an hour. Getting calls down from Mazurk and the crew doing well. And once the third stage is done and delivers the Soyuz to orbit, the spacecraft will again execute all of those pre-programmed commands to get out a number of antennas and deploy the solar arrays. Again, the third stage should fire until about the 8-minute and 45-second mark post-launch. So we should be approaching that very soon. The third stage has cut off, getting confirmation it has separated, and confirmation of Soyuz spacecraft separation, the Soyuz now in orbit.
This is Baikonur lead. Congratulations on the successful insertion, and I would like to give the floor to Mission Control Moscow. Yes, we confirm the separation. Everything was nominal. Thank you very much, and we're working with Moscow Mission Control. Now, this is Mission Control Moscow. How to copy? These are Altairs. We copy you loud and clear. That's great. We are standing by for your KO report, and we are standing by for further operations. Copy all.
And again, a successful orbital insertion. The Soyuz now in orbit, and got confirmation all of the antennas and the solar arrays have deployed successfully. So textbook launch for this rocket today, delivering the crew into its initial orbit of about 126 statute miles. The third stage cut off and dropped away. It performs an avoidance maneuver by opening a valve on its liquid oxygen tank and then falls back through the Earth's atmosphere. But the Soyuz now in its preliminary orbit, and that orbit is going to get raised over the next 6 hours. Control has now been passed over to the Russian Mission Control Center in Koryov. We're going to oversee these 3 crew members as they chase down the International Space Station. Just a few kilometers away now from the International Space Station, and pretty soon is going to be going through all the final phases as it makes its final approach, ultimately docking to the Poisk module on the station. This is a module facing towards space, so on the top side of the station, also known as the Mini Research Module number 2, and they're scheduled to dock there in 40 minutes, 37 seconds and counting, all of that being done automatically. And we're already starting to get great view from the Soyuz itself, showing the crosshairs with the station almost dead in the center there as it is continuing to approach. There's a lot of data on the screen here. 2 things just to really pay attention to in the bottom left corner. One that says, I think, 5.46 and counting down right now. That's how far away they are. So they're about 5.4 kilometers still away from the International Space Station. The number just below that is the rate of closures, basically how quickly they're approaching the station, and that's in meters per second. So right now approaching at about 8.6 meters per second, just over the southeastern part, just about to fly over Melbourne actually in Australia. The Tasman Sea just about to come into view while this Soyuz continues to close in, coming up on just about a half a kilometer away.
560 meters meters is the current range, and the rate is 153, and the word S is nominal.
The Soyuz continuing to fly around. It's a little under 200 meters away from the station right now. Should be starting station keeping in about a minute or so. Again, the Soyuz flying automatically, that Kurs rendezvous system driving the vehicle towards that docking port. Should just be a few minutes away from that initial contact and capture. Some shadows beginning to crop up on the vehicle. The sun actually about to set on the International Space Station while it's flying over the southern Pacific Ocean right now.
Proceed, please, with the report. The diameter of the docking port is 2 squares, 30 meters, 0.14 is the rate. The target is in the center of the periscope. Copy. 2.5 squares is the diameter of the docking port. The target is half of the square to the right of the crosshairs. Range is 10 meters. The rate is 0.12, and a square and a half is the target. The target is in the center of the periscope. The crosshairs are aligned. Copy. 2.5 squares is the length. The target is in the middle.
Single digits, just 9 meters away. Very close now to docking. We'll get you an exact time, but very close now for the Soyuz docking to the Poisk module.
So the target length is 3 squares.
Standing by for contact and capture.
We're standing by for the contact, Moscow. Contact. We have mechanical contact, and we have docking mechanism engaged. Great. Copy.
And you heard it, contacting captured, docking confirmed. 9:55 p.m. Central Time, 10:55 p.m. Eastern Time, while the International Space Station flew about 255 statute miles over the southern Pacific Ocean, just to the west of Chile.
The arrival of the new crew members restores the station's full complement to 6. The new Expedition 53 crew members' arrival also marks the first long-term increase in crew size on the US segment from 3 to 4, allowing NASA to maximise the amount of time dedicated to scientific research. The crew will conduct more than 250 science experiments over the next 6 months. They'll also be conducting some studies into new technologies, such as the benefits of manufacturing fibre optic filaments in microgravity. Other studies will focus on medical research in human spaceflight. These include slowing down or possibly even reversing muscle atrophy in astronauts on long-duration spaceflight, and exploring the ability of a synthetic bone material that adheres bone to metal within minutes to accelerate bone repair. During their stay on station, crew members will also receive Orbital's next commercial resupply mission slated for launch in November. It'll deliver several tons of supplies, research and vehicle hardware. The new crew will remain on station until February 2018. I'm Stuart Gary. You're listening to SpaceTime. It's been a busy time for Russia, with both the manned Soyuz flight to the space station and a Proton-M rocket successfully launching also from the Baikonur Cosmodrome, this one carrying the Amazonias 5 telecommunications satellite into geostationary transfer orbit. The mission was only the third for Proton since its latest return to flight status, following its latest grounding after a string of recent failures. The Proton launch went smoothly, just as planned. The Proton's first stage uses an unusual design, featuring a central oxidizer tank surrounded by 6 outboard unsymmetrical dimethylhydrazine fuel tanks, each fitted with a single RD-276 engine burning for 126 seconds. The Proton's upper stages use more conventional cylindrical designs, with the second stage powered by a single RD-0211 and 3 RD-0210 engines firing for a total of 208 seconds. While the third stage uses a 4-nozzle Vernier engine and a single RD-0213 engine igniting for 238 seconds. 9 minutes after launch, the Proton delivered the Breeze-M upper stage and its satellite payload into geostationary transfer orbit. The Breeze-M then took a series of 5 separate engine burns over 9 hours, placing the Amazonias 5 into its final orbital position. Built in Palo Alto, California, and based on the Space Systems L'Oreal 1300 platform, the 5,900-kilogram Amazonas 5 is Latin America's first satellite with a high-throughput payload for both television and broadband internet services. It's equipped with 34 Ka-band spot beams and 24 Ku-band transponders. The satellite, which has a footprint covering Brazil and Latin America, carries enough fuel for a 15-year lifespan. You're listening to Space Time. I'm Stuart Gary. And time now to take a brief look at some of the other stories making news in science this week with a science report. And a new study claims patients with age-related macular degeneration carry signs of the disease in their blood, which can be detected through laboratory testing. Age-related macular degeneration is the leading cause of adult blindness in the developed world for people aged over 50. The findings, reported in the journal Ophthalmology, describes a new technique known as metabolomics, which can identify blood profiles associated with age-related macular degeneration as well as its level of severity. These potential lipid biomarkers in human blood plasma may lead to earlier diagnosis, better prognostic information, and more precise treatment. Because the signs and symptoms of early-stage age-related macular degeneration are very subtle, with visual symptoms only becoming more apparent at more advanced stages in the disease, identification of biomarkers in human blood plasma may allow scientists to better understand the early to intermediate stages of the disease, allowing earlier intervention. Age-related macular degeneration has recognized genetic and lifestyle risk factors, including diet and smoking status. But the field currently lacks reliable measures to identify patients who may be at risk of developing the disease, including those who may progress to advanced blinding forms of the disease. Researchers reached their conclusions by studying 90 blood samples from participants at various stages of age-related macular degeneration. These included 30 with early-stage disease, 30 at an intermediate stage, and 30 with late stage. These were then compared to 30 samples from patients without age-related macular degeneration. Scientists found 87 metabolites, that's small molecules in the blood, which were significantly different between subjects with age-related macular degeneration and those without. They also detected varying characteristics between the blood profiles of each stage of the disease. Of the 87 molecules identified, most belonged to the lipid pathway. In fact, 6 of the 7 most significant metabolites were identified as lipids. Previous research had already suggested that lipids may be involved in the development of age-related macular degeneration, although the exact role the lipids play in the disease remains unclear. The new results could provide insights into the roles the lipids are playing in the disease, which could then provide novel targets for early-stage treatment. Some 97% of scientific papers have confirmed that climate change is real and is caused by human activity such as burning fossil fuels. Of course, climate change deniers, usually supported by the fossil fuel industry, focus on the other 3%, raising doubt on the entire issue. It's exactly the same tactic used by the tobacco industry to argue against the link between smoking and cancer. In fact, it's even the same people heading the campaign. The basic strategy is a simple one. If you can't fight the facts, just try to raise doubt. But what about that other 3% of reports that do reject climate change? Well, a new study has re-examined these papers in minute detail to see just how legitimate their claims really were. And the evidence shows they were all flawed, either being biased in their reporting or otherwise faulty. The new report in the journal Theoretical and Applied Climatology by scientists from the Norwegian Meteorological Institute and the Texas Technology University examined 38 papers which were denying that humans contributed to global warming. Researchers found that all these studies contained serious errors in their assumptions, methodology or analysis, resulting in scientists being unable to replicate their findings. And that's important because being able to replicate another team's research is the foundation stone of the scientific peer review process. Researchers also found that when mistakes in these 38 papers were corrected, their results were in line with the overwhelming scientific consensus. The authors found the papers were only selecting results that supported the conclusion being sought after and consistently ignored the broader context or other data, including a full-blown disregard for physics. A new study has found that 85% of people living with HIV/AIDS suffer from chronic pain. The findings, reported in the journal Clinical Infectious Diseases, recommends that all people living with HIV/AIDS should now be assessed for chronic pain. The study found that because HIV clinicians are typically not experts in pain management, they need to work more closely with others such as pain specialists, psychiatrists and physical therapists in order to help alleviate their patients' suffering. The study's new comprehensive guidelines provide tools and resources HIV specialists will need in order to treat these often complex patients, many of whom struggle with depression, substance use disorders and of other health conditions such as diabetes. The study recommends those that screen positive should undergo comprehensive evaluation, including a physical exam, psychosocial evaluation, and diagnostic testing. Nearly half of chronic pain in people with HIV is neuropathic, in other words, nerve pain, likely due to inflammation or injury in the central or peripheral nervous system caused by infection. Non-neuropathic pain typically is musculoskeletal, such as lower back pain and osteoarthritis in joints. The study warns that an aging population and changing clinical manifestations of HIV, complexity of the disease and additional challenges related to substance abuse makes treatment more complicated. Scientists at the United States Army Research Laboratory have observed an unexpected result when combining urine with a newly engineered nanoparticle based on aluminum. They discovered it instantly releases hydrogen from the urine at twice the rate of ordinary water. The research team had earlier developed a nanogalvanic aluminum-based powder to produce pure hydrogen when coming into contact with any liquid containing water. Hydrogen is the most plentiful element in the universe, and it has the potential to power fuel cells, providing a unique energy source to power equipment for soldiers in the field. Fuel cells can generate electricity quietly, efficiently, and without pollution. The United States Department of Energy says fuel cells are more energy efficient than combustion engines, and the hydrogen used to power them can come from a variety of sources. Researchers have calculated that 1 kilogram of aluminum powder can produce 220 kilowatts of energy in just 3 minutes. Finding ways to provide power and energy is becoming increasingly important to run communications and electronics gear for away teams that can't be resupplied. So, using urine as a fuel source could well provide many benefits for the forward deployment of troops using equipment with high energy consumption. Mind you, scientists still haven't determined exactly why the urine's causing a faster reaction, but it may have something to do with the electrolytes and the acidity of the liquid. And finally for now, new research claims a mysterious ancient creature known as Dickinsonia was an early member of the animal kingdom. Dickinsonia lived more than 550 million years ago. It's only known through fossils and has variously been described as looking a little bit like a jellyfish, a little bit like a worm, or possibly even a fungus or a lichen. But questions have always remained about whether this mysterious creature was really part of the animal kingdom or something else. Now a new report in the journal Proceedings of the Royal Society B provides the strongest proof yet that Dickinsonia really was an animal. It also confirms recent findings suggesting that animals evolved millions of years before the so-called Cambrian explosion of animal life. The new studies concluded that Dickinsonia belongs to the Ediacaran biota, a collection of mostly soft-bodied organisms that lived in global oceans between about 580 and 540 million years ago. They're mysterious because despite there being around 200 different species, very few of them resemble any known living or extinct organism. Therefore, what they were and how they relate to modern organisms has been a long-standing paleontological mystery. Back in 1947, Dickinsonia became one of the first described Ediacaran fossils and was initially thought to be an organism similar to a jellyfish. Since then, its strange body plan's been compared to that of several primitive animals, as well as several non-animals as well, including fungi, lichen, and even some entirely extinct groups. Discriminating between these different hypotheses has been difficult because there are so few morphological features in Dickinsonia to compare with modern organisms. So instead, researchers have tried to look at how it grew in order to work out how to classify it from a purely developmental perspective. The research was carried out on the basis of a widely held assumption that growth and development are conserved within lineages. In other words, the way a group of organisms grows today would not have changed significantly from the way its ancestors grew millions of years ago. Dickinsonia is composed of multiple units that run down the length of its body. The researchers counted the number of these units in multiple specimens, measured their lengths, and plotted these against the relative age of the unit, assuming growth from a particular end of the organism. This data produced a plot with a series of curves, each of which tracked how the organism changed in size and number of units with age, enabling researchers to produce a computer-based model to replicate growth in the organism and test previous hypotheses about where and how growth occurred. Researchers determined that Dickinsonia grows by both adding and inflating discrete units in its body along its central axis. But they also recognised that there was a switch in the rate of unit addition versus inflation at a certain point in its life cycle. All previous studies assumed that it grew from the end where each unit was smallest and was therefore considered to be the youngest. The researchers tested this assumption and interpreted the data with growth assumed to be from both ends, eventually coming to the conclusion that for the past 70 years, people have been interpreting Dickinsonia as having grown from the wrong end. When they combined this growth data with previously obtained information on how Dickinsonia moved, as well as some of its morphological features, they were able to reject all non-animal possibilities for its original biological affinity and show that it really was an early animal, belonging to either the Plesiozoa or the Metazoa. The findings represent one of the first occasions that a member of the Ediacaran biota has been identified as an animal on the basis of positive evidence. You're listening to Space Time. I'm Stuart Gary. And that's the show for now. You can subscribe and download SpaceTime as a free twice-weekly podcast through iTunes, Stitcher, Bytes.com, Pocket Casts, SoundCloud, YouTube, Audio Boom, your favourite podcast download provider, or direct from spacetimewithstuartgary.com. The show's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C., around the world on TuneIn Radio, and as part of Virgin Australia's in-flight entertainment. If you want more space time, check out our blog where you'll find all the stuff we couldn't fit in the show, as well as loads of images, news stories, videos, and other things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word and in lowercase, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, and on Facebook, just go to www.facebook.com/Spacetime with Stuart Gary. Spacetime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to Spacetime with Stuart Gary. Subscribe at iTunes, Stitcher, Pocket Casts, or Audio Boom. This has been another quality podcast production from Bytes.com.
This episode of Spacetime has been brought to you by Brilliant.org. Maths and science done right. Remember, use our special link so they know you came from here. That's Brilliant.org/Stuart Gary.